Now, in chapter 3, we shall study about Riemannian space. In this chapter, in module 1, we shall discuss about metric tensor, associated tensors, magnitude of vectors and angle between two non-null vectors. In our earlier days, that is in coordinate geometry, we have learned the distance formula d square equals to root over x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. In differential form, that can be expressed as d square equal to dx1 square plus dx2 square plus dx3 square, where dxi's are contravariant vectors. So, in first section, we shall see that how these dxi's change in Riemannian space and the distance formula will change accordingly. So, in chapter 3, the Riemannian space, in module 1, we learned about the metric tensor first, then associated tensors. Now, in orthogonal Cartesian coordinate system, if I denote this one by x bar I, the distance between two neighboring points can be obtained by using Pythagoras theorem. D square equals to d x bar 1 square plus d x bar 2 square plus d x bar 3 square, which can be written in index system d x bar I into d x bar I, where I is running from 1 to 3. Now, this is called a line element, or we can say arc length also, and which is invariant, since the distance between the two neighboring point is independent of the coordinate system. So, if we change the coordinate system, the arc length or the distance will remain invariant. The idea of distance was extended by German mathematician Bernhard Riemann near about in the year 1859 to a space of dimension n denoted by Sn, and which can be expressed as d square equal to gij dxi dxj, where ij is running from 1 to n. Now, this expression is coming by using the covariant transformation to dx bar I, where this gij is coming like this, del x bar m by del xi del x bar m by del xj, the product of two partial derivatives, and these are the functions of xi such that the determinant of gij is not equal to 0. Now, if the determinant gij is not equal to 0 and if it is always positive, then we name the space as Riemannian space. This quadratic differential form gij dxi dxj, which represents the square of the distance between two neighboring points, in Sn is called the metric or Riemannian metric after the name of Riemann. Now, these Gij's are called the metric tensor or the fundamental metric tensor, and they are the covariant tensor of type 02, and it is a symmetric tensor as it is the product of two partial derivatives, and we know that the partial derivatives of a function is a covariant vector. So, Gij's are the tensor of type 02 or covariant tensor of rank 2, and this n-dimensional space Sn equipped with such a metric is called a Riemannian space. For Riemannian space, Gij's is considered to be positive definite. Just I have mentioned earlier that for Riemannian space, Gij is considered to be positive definite. Now, we shall prove this theorem that the fundamental tensor or the metric tensor is a symmetric covariant tensor of order 2 or of type 02. So, we can prove it in this way. Now, with respect to a change of coordinate transformation xi to x bar I, let the metric Gij dxi dxj be transformed to g bar mn dx bar m dx bar n. So, when the coordinate transformation is done from xi to x bar I system, the metric will change in this way: Gij dxi dxj will change to g bar mn dx bar m dx bar n. Now, as d square is invariant, so they are equal. So, if we use the transformation law for contravariant vectors, we get the expression Gij dxi dxj equals to g bar mn del x bar m by del xi dxi del x bar n by del xj dxj, which can be expressed in this form: Gij minus g bar mn del x bar m del xi del x bar n del xj dxi dxj equals to 0. Now, since dxi dxj are arbitrary contravariant vector, so they are not equal to 0, and therefore, we have Gij equals to del x bar m del xi del x bar n del xj g bar mn. So, which is the transformation law for covariant tensor of rank 2, and also the partial derivatives commute. So, we can say that Gij equals to Gji. That means, Gij is a symmetric covariant tensor of order 2 or rank 2, or it is a tensor of type 02. Now, we define the conjugate metric tensor in the following way: G upper ij equals to cofactor of Gij in G by G, provided G equals to determinant of Gij is not equal to 0, and this Gij are conjugate or reciprocal tensor of the fundamental metric tensor Gij, which is also symmetric contravariant tensor of rank 2. It is called contravariant fundamental tensor. Now, let us see an example. If the transformation law from xi coordinate system, which is a cylindrical coordinate system, to yi, that is the Cartesian coordinate system, and the relation is given by y1 equals to x1 cos x2, y2 equals to x1 sin x2, and y3 equals to x3. Then we are going to find the fundamental metric tensor for cylindrical coordinate system. So, by the transformation law, we have the relation y1 equal to x1 cos x2, y2 equal to x1 sin x2, and y3 equal to x3. So, if we calculate G11, it will be del ya del x1 del ya del x1, where a will run from 1 to 3, and we are getting that G11 equals to 1. In similar manner, we can get that G22 equals to x1 square, G33 equals to 1, and G12, G13 and G23 are all 0. Therefore, in cylindrical coordinate system, the line element becomes d square equal to gab dxa dxb, that is equal to gaa dxa square, because all gab when a not equal to b are zeros. So, it takes the form like this: dx1 square plus x1 square dx2 square plus dx3 square. So, in cylinder, if we want to find the distance between 2 points, then we have to use this formula, that ds square equals to dx1 square plus x1 square dx2 square plus dx3 square. Now, let us see another example, that is for spherical polar coordinate system. That is, if we want to find the distance between 2 points on a sphere, then how the distance formula will behave. Now, this is the formula ds square equal to dx square plus dy square plus dz square in the Cartesian coordinate system, where G11, G22, G33 equal to 1 and the Gij's are 0 for I not equal to j. The transformation law for Gij is this one: G dash Ij equals to del xa del x dash I del xb del x dash j Gab, and this is when a equal to b, we get del xa del x dash I del xa del x dash j Gaa, because for a not equal to b the others are 0, and here G11, G22, G33 equals to 1. So, G dash Ij will take the form del xa del x dash I del xa del x dash j. Now, for the spherical transformation, x equals to r sin theta cos phi, y equal to r sin theta sin phi, and z equal to r cos theta is the transformation rule, where r is the radius of the sphere. Now, if we denote in this following way, that x1 equal to x, x2 equal to y and x3 equal to z, and x dash 1 equal to r, x dash 2 equals to theta and x dash 3 equal to phi, then the equation 1 becomes G dash 1 1 equals to del xa del x dash 1 del xa del x dash 1, where a is running from 1 to 3. So, the expression will be this way: del x1 del x dash 1 square plus del x2 del x dash 1 square plus del x 3 del x dash 1 square, and the value of g dash 1 1 is coming to 1. In similar manner, we can calculate g dash 2 2, which is coming to r square, and g dash 3 3, that is equal to r square sin square theta, and the others g I j's, g dash I j's are 0, that is g dash 1 2, g dash 1 3 and g dash 2 3 are all 0. Therefore, in spherical coordinate system, the line element becomes d square equal to g dash a b dx dash a dx dash b, and which takes the form g dash a dx dash a whole square, which comes to this one dr square plus r square d theta square plus r square sin square theta d phi square. So, on a sphere, if we want to find the distance between 2 points, then we have to use this formula, that d square equal to dr square plus r square d theta square plus r square sin square theta d phi square. Now, let us see another example. It is for an arbitrary 2-dimensional space. If g I j is defined as I plus j, then we have to find the upper g I j's, that is the conjugate metric tensor g I j. How to find this one? So, from the definition of g I j, that is equal to I plus j, we get g 1 1 2, g 1 2 3, g 2 1 3 and g 2 2 4, and the determinant of g I j is equal to minus 1, which is not equal to 0. So, we can have, by the definition of conjugate metric tensor g I j, the cofactor of g I j in g by g, provided g not equal to 0. So, we get g 1 1 equals to minus 4, g 1 2 equals to 3, that is equal to g 2 1, and g 2 2 equals to minus 2. In previous section, we have learnt about the metric tensor, or which is called the fundamental metric tensor for a Riemannian space, which is denoted by g I j's. Now, in this section, we shall learn about some applications of this fundamental metric tensor. With this fundamental metric tensor, we can find the distance between 2 points in an arbitrary space. By these g I j's, we can get some other things also. First of all, we can see that we can obtain the associated vectors of a Riemannian space. So, g I j are used to find the associated vector of a contravariant vector or associated vector of covariant vector. So, this section is named as the associated vectors. So, let us start with the definition of associated vectors. Now, suppose A m1 m2 mp and n1 nq is a component of a tensor of type PQ, then the tensor obtained by performing inner product with the metric tensor Gij and its conjugate G upper ij are called the associated tensors of the given tensor. So, if Aj is a contravariant vector and Bk is a covariant vector in xi coordinate system, then A lower I equals to Gij A upper j. That means, A lower I is a covariant vector which is the associated covariant vector of the contravariant vector Aj. Similarly, B upper I equals to G I k B k. That means, B I are the components of a contravariant vector which is the associated vector of a covariant vector with component B k. So, here A lower j and A upper I are called mutually associated vectors. Now, let us see the relation between the pairs of the associated tensors B T P q and B T R q. So, B T P q can be expressed in this form G R P B T R q. So, inner product of G R P and B T R q. Now, we see another example, that if A k equals to G upper I k A I, then the associated vector A m will be G k m A k, and conversely. So, let us see the solution. We can write A k equals to G I k A I. Now, inner multiplication on both sides with G k m to the above expression, we get G k m A k equals to G k m G I k A I, and G k m G I k, that is the inner product of G k m and G I k will give del I m A I, and by using the index notation we get that is equal to A m. So, this is the proof of the relation that A m equals to G k m A k, and converse also follows in the similar manner. So, in chapter 3's first module, we have learned about two things. In the first section, we have learned the distance formula and the concept of fundamental metric tensor Gij. So, with that formula, we can obtain the distance between 2 points in a Riemannian space. Secondly, we have learned the concept of associated tensors and vectors with the help of this fundamental metric tensor. We have seen that associated tensor or vector of a contravariant vector is a covariant vector, and associated vector of a covariant vector is a contravariant vector. With this, we finish the module 1 of chapter 3.